Hi everyone. In the previous lecture, we discussed about the IV characteristics of a MOS device, and then from that we derived the small signal model of a MOS device. So shown here is a 3-terminal MOS device with the gate to source as the input voltage and the drain current as the output current and the drain to source voltage VDS as the output voltage. We discussed two IV characteristics graphs. The first one here shown here is a transfer characteristics, which represents the change in the drain current to an input voltage, which happens to be the gate to source voltage. So it's the response at the output in response to the output in response to an input gate to source voltage. And then we also discussed the output characteristics, which plots the output current with respect to the output voltage. To a first order, we said the output current in a region called as the saturation region. We discussed that in that region the output current is independent of the output voltage, and if you change the input voltage, which is the gate to source voltage, the output current increases. So in a sense what we said is that in this region we said, so and this region is nothing but the voltage, output voltage VDS is greater than VGS minus VTN. So for this voltage we said that the drain current is independent of the drain to source voltage and it only depends upon the gate to source voltage. So therefore in this region the MOSFET behaves as a voltage controlled current source. And we discussed that if you can design a voltage controlled current source, then you can use such a device to build an amplifier. So and we discussed one of the simplest and the important equation in the MOS device physics lecture. So which is the simple square law characteristics in saturation region. So we said you have to bias your MOS device in saturation region for it to behave as an amplifier. And in saturation region, the drain current has a square law dependence on the gate to source voltage. So this directly follows from the transfer characteristics. And this equation holds true for VDS greater than VGS minus VTN. If VGS is less than VGS minus VTN, we'll have to use the ohmic region or linear region equation, which we have discussed in the previous lecture. So the drain current is given by beta n by 2 into VGS minus VTN the whole square, and we call this term VGS minus VTN as V over drive. And beta n here is simply mu n Cox W by L. And we said the problem of amplifier design involves two parts. The first part is biasing the amplifier. Now once you bias the amplifier, so usually when you design an amplifier, you design this amplifier for a certain voltage gain. Now how does one know what is the gain that this amplifier will actually give us? So that gain is normally estimated from a small signal model. So in the small signal model, the small signal model parameters for this MOSFET can be obtained from the transfer and the output characteristics. Now if you see this MOS device, it's a 3-terminal device, and we said that by looking at the output characteristics we can instantly see that the output current flowing between drain and source is a voltage controlled current source. And that is what we have represented here in the small signal model. So at the output you have a voltage controlled current source, and at the input, since it's the gate terminal of a MOS device, the gate current is 0. So I have represented between gate and source it's an infinite input impedance, but rather there is no current, for even if the gate to source voltage is finite, since there is no gate current flowing through the gate terminal, and because it happens to be an insulator, there is an oxide in between. So we say that we represent it as an open circuit. And the third important parameter we discussed in the last class is R naught, which is actually, we said that in this region or in the saturation region, the drain current actually increases gradually as you increase your drain to source voltage. And we introduced a term called the channel length modulation parameter lambda, and we said the slope in this region, it's called GDS, which is dou ID upon dou VDS, which was equal to lambda times the quiescent drain current. And we said R naught, the resistance, the output resistance when the device is in saturation is given by 1 by GDS, which is 1 by lambda IDQ. So that's what is shown here in the small signal model. So once you know the drain current, you can estimate the small signal parameters of the MOS device. So 3-terminal MOS device is represented in this model that's shown here. The transconductance GM, that's a transfer parameter, so that you have to obtain it from the transfer characteristics. So the GM is simply dou ID upon dou VGS, and that we discussed in the last class that the GM has three expressions in terms of the drain current, overdrive voltage and beta n, which is the W by L. The first expression is 2 ID upon V overdrive, and the second one is beta times V overdrive. The third one is root of 2 ID beta into beta n. So, and we said we will be using all these three equations interchangeably as necessary when we are analyzing these MOS circuits. And we also said how does GM change by changing the drain current or the overdrive voltages. For example, if I fixed the overdrive voltage, so if I applied a fixed DC voltage source between gate and source and I just kept blindly increasing W by L. So if I fixed VDC, which means V overdrive is fixed, and I'm just increasing W by L, then one can intuitively see from this equation, the second equation, that as you increase W by L, your drain current is increasing as well, because your overdrive is fixed, so drain current is also increasing, so your transconductance will actually double. So we can directly see that from this equation itself, the beta n into VGS minus VT whole square, if I have double W by L, ID is also going to increase. Okay, so slope of that curve will also increase by factor of 2. We just very briefly discussed all these things in the previous lecture, so I'll not talk much about that now. And the one thing that we missed in the small signal model, when we spoke about the small signal model in the last class, was the bulk terminal. How is a bulk terminal captured in the small signal model? So we said in the previous lecture that for a bulk terminal, naturally, if you see, you have two diodes formed between source to bulk and drain to bulk. And we said for proper operation, these two diodes should always be reverse biased, which means the bulk should be always connected to the lowest possible potential. In a unipolar supply, where the minimum voltage is 0, maximum voltage is VDD, we connect the bulk always to the lowest voltage, which happens to be ground. But what happens when you don't connect it, or when your source is at a higher voltage? Meaning, in the previous models, we assumed that source and bulk were tied together. When source and bulk are tied together, then the MOSFET was simply a 3-terminal MOSFET, and the small signal model is what we just discussed a few moments ago. But the moment source, in many cases we will see that, for example, in a common gate amplifier and common drain amplifier, which we will discuss at a later stage, source terminal will not always be tied to the bulk terminal. In fact, the source voltage will be at a higher voltage than the bulk terminal. In that case, how does one include this? Is the small signal model really complete? What we have written here, is it really complete? Or what additional model or additional parameters that should be included in this small signal model? To do that, we have to just understand very briefly. I'll first tell what is the addition that we are going to add, and then discuss intuitively why does this current source addition make sense. Now, one can intuitively see that the bulk terminal is also like a gate terminal. So slightly modulating the bulk terminal, one should expect to see a change in the drain to source current. So the model for this bulk terminal is given by GMB. It's the transconductance for the bulk terminal, GMB times VBS. VBS is the bulk to source voltage. So here I have shown another terminal bulk here. Bulk, I have assumed it to be at AC ground right now. Even though it's at the lowest potential, there is no AC signal present there. So I have assumed it to be AC ground. So VBS happens to be the voltage between bulk and source terminal. We model the drain to source current of value given by GMB into VBS, where GMB here is the transfer characteristics, or rather the change in the drain current with respect to the change in the bulk to source voltage. Okay, and generally GMB happens to be smaller than GM. So we'll see how does this translate, how does change in the bulk voltage translates to a modulation or change in the drain current. Very briefly, in an intuitive way. If you look at the structure of a MOS device, Typically, in the previous analysis when we analyzed, we assumed the source and drain were shorted together, so that this diode, this PN junction diode, had a 0 volts across it. But now imagine a scenario where the drain voltage is held at a higher voltage, which is 1 volt, and source is also held at 1 volt, and the bulk terminal is held at 0 volts. Now what happens here is that the diodes, both source end and the drain end diodes, the reverse bias voltage across these diodes increases. If the reverse bias voltage across this increases, there will be more depletion charge. Now that we can see this as an effect, as though it is robbing away some, if there is more depletion charge, meaning there is a charge here, and this charge is actually robbing away some free electrons in the channel. Now because the free electrons are reduced in the channel, we can see that the VT threshold, now you need to actually increase your gate voltage to get back those free electrons. So that is actually, it can be seen as an increase in the threshold voltage. So if you increase your source voltage, keeping the bulk voltage at the lowest potential, which happens to be ground, what happens is that your threshold voltage increases slightly. Again, there is a proper mathematics for that. You will find it in any standard book on device physics. So if you increase your source potential, your VT actually increases. Okay, and so my focus is only the intuition part. I'm not even giving the equation, which is very simple equation. By how much does the VT increase? It's a very simple equation. I don't even want to go there. So instead, I'm just intuitively saying that because you're robbing away some electrons here because of the increase in depletion region, threshold voltage is just telling you the number of free electrons available in the channel, where the concentration of the free electrons becomes equal to the bulk doping concentration, the whole concentration in the bulk. So we say roughly when you attain that electron concentration near the surface, we say then we can say that the device is in strong inversion, and that voltage which corresponds to that is a threshold voltage. But now as I increase the source voltage, this diode gets more reverse biased. So the depletion region extends further, eats away a bit of the channel. You will have immobile electrons, and those free electrons concentration will be slightly reduced in the channel. So now I have to apply a slightly more higher gate voltage to get those free electrons back. So which means that can be seen as an increased threshold voltage. So threshold voltage increases if I increase my source voltage. Now what I'll do here is that in the second case, what I've done here is that instead of holding the bulk potential, see, always remember the bulk voltage has to be lowest. It has to be lower than the source voltage. But I'm slightly increasing the bulk voltage to 0.5 volts. If I increase the bulk voltage to 0.5 volts, now these diodes will become less reverse biased. So the depletion width will reduce. So which means more electrons will free up. And this amounts to, by increasing the bulk voltage, if you see what I have done here, is that I have reduced the threshold voltage. Because now the electrons are back, the free electron concentration is slightly higher than what it was in the previous case, which means that amounts to showing intuitively that this corresponds to a slight reduction in the threshold voltage, because now I have more electrons. I don't need to apply a higher gate voltage to get the same number of electrons as what it was the case when source was at 0 volts. Okay, source was at 0 and bulk was at 0. Okay, or sorry, source was at 1 volt and bulk was at 0. So now I can see that I have to apply a slightly lesser gate voltage, so which means that translates to a slight reduction in the threshold voltage. So which means if I increase my bulk voltage, it amounts to VT modulation, meaning your threshold voltage is slightly reduced. Now if your threshold voltage is slightly reduced, for the same gate voltage, you are going to have a larger number of electron concentration between drain and source, which means a larger current between drain and source. So this is how the bulk terminal has an effect. The bulk terminal, as you increase the bulk voltage slightly, you should expect a change in the threshold voltage, and in turn that translates to an increase in the channel charge, or rather an increase in the drain current. So an increase in VBS, bulk voltage with respect to the source voltage, results in an increase in the drain current. So I'll write IDS, drain current, drain to source current, or drain current is proportional to VBS. So we can write it as GMB times VBS. So which is what I've shown mathematically in the model here. So an increase in the drain to source current given by GMB times VBS. So this is the additional model that we had not included in the previous lecture. So if you have a bulk terminal, then you will have an extra current GMB VBS flowing from drain to source. That's it. So there is a very simple intuitive explanation for it. We don't expect you to go through the deeper into the mathematics in this course. Okay. So with this, I have finished the small signal model representation of the MOS device. Now, I'll very briefly solve some problems just to get you familiarized with the square law characteristics. So because we have introduced the square law characteristics or the square law equations for the first time. So quickly to get you familiarized. So here are two problems. The first one is very trivial, second one is little tricky. So we'll try to solve these two problems just to get familiarized with the square law drain characteristics, the drain current equation. So shown here is a MOS device. Substrate is grounded, source is held at 1 volt, gate is held at 3 volts, drain is held at 5 volts. So you're supposed to find the region of operation and the drain current in this MOS device. You can also ignore the VT modulation. See, for example, source voltage is at a higher voltage than ground. So which means VT will be slightly higher compared to what it would have been if source was at 0 volts. So I'm ignoring body effect. So that effect is called body effect. Because of source being at a higher voltage, your VT will increase. So we are neglecting that right now. So I'm going to assume VT is remaining unchanged even when source is at a higher voltage. And that's going to be at 1 volt. So now you're supposed to find the drain current and the region of operation. So first, to find the region of operation, you need to use this condition that VDS should be greater than VGS minus VTN. If this condition is satisfied, then you know the MOS device is in saturation region. Now, I can also write this as, because source is common for both drain and gate, it's a single MOS device, I can write this as VD greater than VG minus VT. So the drain voltage should be greater than VG minus VT. Here the gate voltage is at 3, minus VT is 1, 2 volts. So if your drain voltage is greater than 2 volts, then we can say the device is in saturation region. But now here the drain voltage is at 5 volts, which means the device is in deep saturation region. It's properly biased in saturation. Now because the device is in saturation region, we can immediately use the square law characteristics to write the current. The drain current is given by beta n by 2, which is mu n Cox W by L by 2 into VGS minus VTN the whole square. VGS of this device happens to be VG minus VS. The gate voltage is at 3. So VGS is 3 minus 1, which is 2 volts. So 2 minus VT is 1. So you will get 1 square into beta n by 2. This term is given in the question as 1 milliampere per volt square. So you get 1 milliampere per volt square. So this is 1 milliampere. So this is your drain current is just 1 milliampere. Now coming to the second question. The second question, it's slightly trickier than the first one. And this is something that's very commonly used. We will later discuss circuits called current mirrors, where we talk about matching two MOSFETs, which means we'll have two identical MOSFETs. No two MOSFETs will be identical when you actually fabricate it in an IC. So we will later see, to have a better matching, to realize longer length MOSFETs, we will start connecting MOSFETs in series. So for example, if you look at this MOS structure, it has one drain terminal here, and I have connected two MOSFETs in series. So I can draw this MOSFET this way. So I have MOSFET 1, the first one here, and then the second MOSFET is connected in series. They both share this N plus region. So the drain of the second MOSFET, this is the second MOSFET. So as I said, for a MOSFET, you will count the terminal you will actually treat the terminal which is at a higher voltage as drain and which is a lower voltage as source. For the first MOSFET, since the drain current is going to flow in this direction, the first terminal is drain, this N plus will serve as the source. For the second MOSFET, this will serve as the drain and this terminal will serve as the source terminal. So that's what I've shown here. Now you have two such devices. One can readily see, if I ignore the N plus region here, the width of the N plus region, the electron from this source region has to travel nearly a 2L distance before it reaches the drain, the higher voltage, which is 5 volt region. It has to travel a distance of roughly 2 times L. So which means I can treat this combination, this composite MOS structure as a single MOSFET, width is same. If you look at the third dimension, width is determined in the other dimension, that remains the same, but length is now 2L. So I can treat this as a device of width same but length as 2L. So gate, drain and source. So this here the W by L ratio is W by L, and here it's also W by L. Now what are we supposed to find? We are supposed to find the drain current and the region of operation of the devices. So we will go step by step in this problem and try and find what will be the drain current and the individual region of operation of the individual devices. So before I start with the analysis, so now I have a MOS device. The MOS device, I'm talking about the second problem here. So this source is at 1 volt, the gate is at 3 volts, and we are supposed to find the region of operation for both these MOSFETs. So first let's look at the upper MOSFET, which is the first MOSFET. The drain voltage is 5 volts. The gate voltage is at 3 volts. And since for the condition for this first device to be in saturation is that the drain voltage should be greater than Vg minus Vt. And Vg is at 3 minus 1 Vt, which is equal to 2 volts. If Vd is greater than 2, then the device is in saturation. And since Vd is 5 volts, the device will be very deeply, or it will be in deep saturation. So the first device is in saturation region. Now let's try to find what is the region of operation of the second device. I'm going to call this intermediate node voltage. We don't know what it is yet, so we'll call it as Vx. Now I'll just use a very simple understanding of MOSFET. So if let's say we have a MOS device and it is carrying some current, so we just showed that the upper device is conducting. And if you look at the lower device here, the gate is at 3 volts, source is at 1 volt, so the VGS is at 2 volts, which means VGS is greater than VT. VT is 1 volt, 2 volts is greater than 1 volt, so VGS is greater than 1, which means the lower device is conducting, which means there is some current flowing in both the devices. If a MOSFET is conducting, we can readily say, if you know the gate voltage, the source voltage here will at least be a VT lower, because you need your VGS for this MOSFET will be greater than VT. If the device is conducting, then VGS has to be greater than VTN, which means you can say the source voltage will be less than VG minus VTN. So now immediately I can see that the source gate voltage is at 3 volts for the second device. Okay. I'm sorry, I'm talking about the first device here. So the first device, gate voltage is at 3 volts. So I can immediately say that the source voltage for the first device will be less than 2 volts. 3 minus 1, Vt is 1. So it will be less than 2 volts. So that's something we are aware of. So now I'll come back to this. So we know that the voltage here, this node Vx will be less than 2 volts. So I've redrawn the circuit here. So here you can immediately see that this node voltage will be less than 2 volts. Now the gate voltage is at 3 volts, and the condition for this device to be in saturation is Vg minus Vt. So we will compute Vg minus Vt. We have to compute Vg minus Vt. Vg minus Vt happens to be 3 minus 1, which is 2 volts. But we know the drain voltage here, which is the drain voltage of this the source voltage of the first MOSFET, which is drain voltage of the second MOSFET. We said it can only be less than 2 volts. But the condition for the second device to be in saturation is the drain voltage has to be greater than 2 volts. So therefore, the second device will be in linear region. So now to find this node voltage Vx, there are two very simple procedures. I'll show both the procedures. There is one much simpler procedure. We can employ that to solve it, or one is a little bit the brute force way of solving it. The simpler procedure, I'll go with the simpler procedure, is that we know the two devices are in series. So I can treat this as a single MOSFET of length W by 2L. I can treat this as a single MOSFET of length W by 2L. So this device I'm going to represent as a composite MOSFET. This is the drain terminal, source terminal and gate terminal, but with length 2L. Now we know that the drain current is given by beta n by 2 of this composite MOSFET. So I'll write it as mu n Cox W by L to mu n Cox W by 2L into half into VGS. Here happens to be 2 volts because gate is at 3 and source is at 1 volt. So VGS is 2 volts. 2 minus 1, VT is 1. The whole square will be your drain current. And from the previous problem, we just estimated this term to be 1 milliampere. So now the drain current will be half of the previous problem, which is 0.5 milliamperes. Okay. So the drain current is 0.5 milliamperes. So we know the drain current in this circuit. Now immediately, if I know the drain current, I can easily calculate what this node voltage Vx is going to be. Because I know the drain current and I also know that the first transistor, I just calculated the drain current right now, and the question doesn't ask you to find Vx, but I'm just trying to find what will be the value of Vx. We said Vx is less than 2 volts, but what is that value? To find that, now that I know the current flowing in the device, I also know the first device is in saturation, I can directly use the saturation equation. So which is 0.5 milliampere is the current flowing through that, and the first device, half mu n Cox W by L is its beta n multiplied by VGS minus VTN. We don't know VGS, so VGS here is 3 volts minus Vx. So 3 minus Vx is VGS minus VT will be minus 1 the whole square. So here if you see this term, mu n Cox W by L into half is given as 1 milliampere per volt square. So you will be left with 2 minus Vx the whole square equals half a milliampere. So you will get a result 2 minus Vx equals plus minus 1 by root 2, and so Vx will be equal to 2 minus plus 1 by root 2, but we know Vx is less than 2, so I just discard the solution which is 2 plus 1 by root 2. You are left with 2 minus 1 by root 2, and this will be approximately equal to 2 minus 1 by root 2 is 0.707. I think it is 1.293 or 1.3 approximately. There is also a brute force way of solving it, which is we know the first device is in saturation region, the second device is in linear region. So we just have to equate the two device currents. So the first device is going to carry a current of beta n by 2. So it will be mu n Cox W by L into half into VGS minus VT. So VGS will be 3 minus Vx minus 1. So it will be 2 minus Vx the whole square. This should be equal to the current in this MOSFET, and that will be in linear region. So I'm going to call this as half mu n Cox W by L. So this will be just mu n Cox W by L into VGS minus VT into VDS. VGS minus VT for this device, VGS is 2 volts minus VT is 1, so it will be 1 volt. VGS minus VT is 1 times VDS. VDS for this is Vx minus 1 minus VDS square by 2. So that will be Vx minus 1 the whole square by 2. So now you have a quadratic equation in Vx, and if you solve this, you will get the same answer that we have gotten here. So that's it. So if I want to realize a MOSFET of length 2L, you can easily connect two devices in series this way. Instead of fabricating a single device with length 2L, we can connect these two devices in series. Later we will see, when we talk about current mirrors, how such a arrangement helps us in getting better matching. So I'll introduce all of those ideas when we discuss about current mirrors. Then we'll take two very trivial problems, and again these are all trivial now, but when you learn it for the first time it may not be, but these are all pretty simple problems on getting you familiarized with the the drain current equations of a MOSFET. So in this circuit, a current of 1 milliampere is flowing into the drain terminal of a MOS device, and I have short circuited gate and drain terminal. The moment I short circuit gate and drain, so we have this condition VGS is equal to VDS, and you are supposed to find the node voltage, drain node voltage with respect to ground, and that is simply VDS itself. You are supposed to find VDS in this problem, and we said VDS is exactly equal to VGS. So whenever you want to find the drain current equation, we need to know what drain current to apply. We have two equations for the drain current for a MOSFET, depending on the region of operation. Now immediately first thing you have to do is find the region of operation. Here VGS equals VDS. Because your VGS is equal to VDS, the condition for saturation is that your VDS should be greater than VGS minus VTN. But since we said VGS is equal to VDS, obviously this VDS will be greater than VGS minus VTN. Okay, so therefore this device will be in saturation region. Similarly, for the PMOS device, the conditions, or you can directly take modulus and apply them, so which means mod of VDS should be greater than mod of VGS minus mod VTP, or in a more accurate way, VSD, because source is at a higher potential, should be greater than VSG minus mod VTP. This is the condition for saturation in a PMOS device. Now you can directly see here, this is your gate terminal. Your gate and drain are short circuited, so therefore VSD equals VSG. Gate and drain are short circuited, so therefore V source to gate will be exactly equal to source to drain voltage, which means this condition will be easily satisfied because VSD is equal to VSG minus VSG, so it will obviously be greater than, this will be greater than VSG minus VT. If you subtract a VT out, this node voltage is going to be greater. So therefore this device is also in saturation. So once it is in saturation, we can directly apply the square law equations and find the voltages. So I'll directly give those values here. The values are given here. Mu and Cox is 100, W by L of NMOS is and PMOS are 10, mu P Cox is given as 50. So you can just directly use the square law equation and calculate the voltage Vx. So here you will have the drain current ID happens to be equal to beta n by 2 into VGS, which is in this example is same as VDS, which is also equal to Vx. So it will be VGS minus VTN the whole square. Drain current is 1 milliampere. You can directly solve this equation. Beta n is fully given. Beta n is mu n Cox into W by L n. It's given to you. So from that you can easily calculate the value of Vx. Okay, the value of Vx turns out to be root 2 plus 0.5. Similarly, you can, in a very similar way, you can find the voltage Vx in this circuit here. So in this circuit, for the PMOS device on the other hand, so I'll write the expression for the drain current in the PMOS device. For the PMOS device, the drain current is given by beta P by 2 into mod of into VSGP minus mod of VTP, the whole square. And VSG, source to gate, for this PMOS device, voltage is source is at VDD, which is 3 volts. I think it's 2 volts in this question. So source is at 2 volts. And this terminal, gate terminal, we are calling it as Vx. So this will be 2 minus Vx. So it will be beta P here. Beta P is 50 micro into 10. So you'll have 500 microampere per volt square. So or 0.5 milliampere per volt square. Into 2 minus Vt is 0.5. So you'll have 1.5 minus Vx the whole square. Okay, this is equal to 1 milliampere. So from that we can actually easily estimate what will be the value of there is also a half factor here, half factor. So we can easily find out what should be the value. You will get Vx as minus 0.5 volts. So in fact you will get Vx 1.5 minus Vx as 2 volts. So Vx you will get it as minus 0.5 volts. So now finally I've taken another very simple circuit. So this is since most of you have already done basics of Cmos inverters. So this is a Cmos inverter with input and output short circuited. So we have a PMOS device and an NMOS device whose gates and drains are shorted together. So that's just a static Cmos inverter whose input and output are short circuited. So here you're supposed to find regions of operations of both the devices and the drain current in the circuit. And you're supposed to find the node voltage Vx in the circuit. And the mu n and mu p Cox W by Ls are all given to you. I'll just tell you the approach, and I think it's pretty simple after that. So you're supposed to find the node voltage Vx here. So first we have to quickly understand that So this is nothing but a series of two diode connected NMOS and PMOS devices. So therefore, we saw in the previous problem, if you short circuit drain and gate for NMOS or PMOS device, both the devices will be in saturation region. Since both are in saturation region and they both are in series, so therefore they will carry same currents. So we can directly equate the currents in both the devices. So beta n by 2 into VGS minus VTN the whole square will be equal to beta p by 2 into VSGP minus mod VTP the whole square. And in the question it's given in such a way, the product mu n Cox W by L n is exactly same as mu p Cox W by L p. So 100 into 10 is same as 50 into 20. So both will be 1 milliampere per volt square. So therefore I'm cancelling out beta n and beta p. You are left with this equation. You are left with the condition VGSN minus VTN is equal to VSGP minus mod VTP. I've also given the VTs are same, so they both cancel out. So the VGS and VSG are same. So now if you look at this device, both the gate to source voltages of MOS and the NMOS and PMOS are same. So you have VDD here. So this is VSGP and this node voltage is VGSN. And if you apply KVL in this path, VSGP plus VGSN should be equal to VDD. So you get VSGP plus VGSN should be equal to VDD, and we said they both are equal. So we get VGSN equals VGSP equals VDD by 2. VDD is given as 3 volts, so this will be 1.5 volts. And we can directly see from the question that VGSN happens to be the same as Vx, so Vx is 1.5 volts. So in the next lecture, we'll start with that. So this is just a very introductory lecture on understanding the IV characteristics and using MOSFET's drain current equations and calculations. So the next lecture, we will start with the common source amplifiers. So that's our first introductory lecture on amplification in using MOS devices. Thank you.